Back in the late 1600s, Isaac Newton argued that light was corpuscular, basically made of tiny little particles. But then, fast forward to 1801, Thomas Young performs this brilliant interference experiment that proves light acts exactly like a wave. So, case closed, right? Well, no, not exactly. In 1905, Albert Einstein comes along and shows light actually has discrete particle-like energy. And by the 1920s, Arthur Compton takes it a step further, demonstrating the physical momentum of light particles literally bouncing off targets.
So what is it? Is light a wave, or is it a particle? Well, this mind-bending concept known as wave-particle duality arose as the only possible way to describe the impossible. It means that fundamental entities genuinely exhibit both properties. And here is the kicker. Their behavior is completely dependent on how we set up our experiments to measure them.
Moving on to Section 2, the photoelectric effect, proving the particle. Let's zoom in on exactly how light's particle nature was definitively proven. Back in the late 19th and early 20th centuries, scientists like Heinrich Hertz and Philip Lenard were observing something called the photoelectric effect. Basically, when they shined light on a piece of metal, it ejected electrons. But here was the big mystery. Making a light brighter, just cranking up the intensity, didn't change the maximum energy of those ejected electrons. If light was just a continuous wave washing over the metal, a bigger, brighter wave should mean a much more energetic electron, right? But it didn't. This completely shattered the classical rules of electromagnetism.
It was Einstein who finally solved this puzzle. He proposed that light doesn't act as a continuous wave here, but rather as discrete packets of energy. Quanta, or as we usually call them, photons. He postulated the incredibly famous equation E equals hf, which just means energy is tied directly to frequency. Since blue light has a higher frequency, a single blue photon packs enough of a punch to knock an electron free. But red light? It has a lower frequency, so a red photon just doesn't have the energy. You could literally shine the brightest, most intense red light in the entire universe at that metal, and absolutely nothing would happen. Why? Because the energy is delivered exactly one discrete particle at a time. One photon releases exactly one electron. This definitively cemented light's particle behavior.